All right, welcome back. What's the big picture of this method of substitution? Like, why does it work? And why does it not just work, why does it work so well? What each of these problems that we've seen so far have had is they've had a general structure. They've each had this form. They've all been the antiderivative of a chain rule. Remember, the chain rule, if you take the derivative of f of g of x, so this portion here, d by dx, of a function of g of x, f of g of x, is f prime of g times g prime. So what we're asking for is the antiderivative of the derivative of f of g of x. And we know that derivatives and antiderivatives are opposite operations. When we take the derivative of, let's say, x squared, we get 2x. When we take the antiderivative of that 2x, we get back our x squared plus c. So if I'm taking the derivative of the antiderivative of f of g of x, I'm just going to get f of g of x plus c. Since antiderivative and derivative are kind of opposite operations. They're kind of, I say kind of opposite because there's a plus c that's hanging out there if we do the operations inside this order. And that's what substitution is really doing. It's revealing the composite nature of the function. But the function inside the integral is something that you would get by taking the derivative according to a chain rule. And we're just reversing it. It's to reveal that nature. So here's one that's very general. We have the antiderivative of the sine of f of x times f prime. And I'm going to solve this like we were solving the other ones with the w's. So it doesn't really matter what that f of x is. I'm going to let w equal f of x, the part that's being plugged in. Then dw by dx is f prime of x, and then rearrange. So dx is equal to dw divided by f prime of x. Now we'll have that plugged in. So integral sine of w, and then the dx gets replaced by dw over f. Oh, I forgot the f prime. Sine of w times f prime of x, and then the dx gets replaced dw over f prime of x. Or f primes cancel. It doesn't matter what f prime is. F prime, or it doesn't matter what f of x is. F of x could be some horrible thing with square roots, more trig, exponentials and logs. It could be some nasty expression. Doesn't make any difference. As long as the antiderivative has this structure, a function of f of x times f prime of x, it'll transform very beautifully after we do a substitution. Sine of w, dw. Okay, well, what do we take the derivative of to get sine? It's not cosine. Derivative of cos is negative sine of x. So we need an extra negative in front. Negative cos of w plus our constant of integration. And now we can replace w by f of x. Cos of f of x plus c. And this is true for any f of x. Well, there's some fine print. Any differentiable f of x, any function with a derivative, which is understood to be true because there's an f prime sitting there. Here's another one, test style example. We're not given all the information we need to fully solve this. What we're told, and so that means we're going to get part way, and we'll have to stop part way, and that's okay. We're told that h of x is defined as the antiderivative of f of x. And we're asked, with that information, express this antiderivative. The antiderivative of the cosine of x multiplied by f of 2 sine of x dx. So I'll show you how to do a problem like this. It's very unusual. It's extremely useful though. We have two parts to use a substitution for. We have the cosine of x and we have the 2 sine of x. I'm going to use 2 sine of x for the substitution because that's the part that's being plugged into the function. So I'm going to let w equal 2 times the sine of x. Now I'll take the derivative, knowing in advance I have to replace the dx. dw by dx is 2 times the cosine of x. And then rearrange to get the dx. dx is equal to dw over 2 times the cosine of x. I'm going to plug that in. So integral cosine of x is a problem. We have f of w. We don't want to have a mixture of x's and w's, so we really need that x stuff to cancel. Unfortunately, it does. dw over 2 times the cosine of x. So cos on top cancels with cos on the bottom. I'm going to take the 2 that's in the denominator and bring it out front as a 1/2. 1/2 times the antiderivative of f of w dw. This is the part that nobody likes. H of x is defined as the antiderivative of f of x dx. So what's the antiderivative of f of w dw? Well, we're just changing the letter of the alphabet. It's just going to be h of w. So 1/2 h of w plus c. I'll put the reasoning, since antiderivative of f of x dx is equal to h of x. Just change the letter of the alphabet. You can imagine just swapping the order in the alphabet song, x with w, just changing where they are. In another universe, that's their letter in that position. Okay, and now we can go back to undo the substitution. We can let w equal 2 sine of x. So 1/2 times h of 2 sine of x plus c. So we're posing our solution in terms of its relationship to the earlier solution, to h of x. So you modify the function inside, you multiply it by something that's related to the derivative of what's inside, and you can express your new antiderivative in terms of your old one. All right, and here's some more normal examples. So this is a classic problem, the antiderivative of e to the x divided by e to the x. We have a root x in the denominator and root x in the power. I'm going to let w equal the one that's being plugged into the power. They're the same, so in this case it doesn't matter, but I'm just telling you where my reasoning is coming from. I'm picking that one as the justification for the substitution. I'm not picking the denominator as the justification. Now let's rewrite everything. Something weird is going to happen here. We're going to e to the w over w. I'm going to replace the dx. So we have to take the derivative of w, dw by dx. Square root x means x to 1/2, so we take the derivative 1/2 x to the negative 1/2. I'm going to rewrite that as 1 over 2 root x. But root x is w, remember? So 1 over 2w. We're using the substitution again. Now I'm going to cross multiply, so 2w dw is equal to dx. and sub that in over here. Now we have a w on top that cancels the w on the bottom. And the integral is nice, just antiderivative of e to the w. Antiderivative of e to the w is e to the w plus c. And then we can plug in, oh, I forgot the 2. Where's my 2? So 2, there's a 2, 2 e to the root x. Oh man, I'm having some writing problems. Root x plus c. There you have it. And you can check the derivative of that expression after you simplify the derivative is going to be e to the root of x over the root of x. All right, here's another one that's something else weird will happen here. Here we have two things that are being plugged in somewhere. We have tan that's being plugged into power 2, and we have secant that's being plugged into power 2. I'm going to rewrite it. Integral of tan of x all squared times secant of x all squared, just as a reminder of what that power 2 notation means. We have two candidates for our substitution. We have w is equal to tan of x, and we have w is equal to secant of x. I'm going to try the wrong one first to show you what does a bad substitution look like. Bad sub. And you know, the only reason I know it's bad is because I've done it before. I've tried it before and it didn't work. And when you're doing them, you're not going to know ahead of time, is this the good one or is this the bad one? So you have to be able to do the bad one and recover from it and say, okay, well, it's the other one then. It's not the end of the world to make it. It's not even a mistake. You're just trying out a strategy. So I'm going to let w equal w equals secant is the bad one. W is equal to secant of x. So that allows me to rewrite the expression. I have a tan of x that's still there. Now secant of x becomes w squared. Secant of x squared becomes w squared. Now I've got to replace the dx. So I'm going to take a derivative. dw by dx. Derivative of secant of x is sec x tan x. And rearrange to get dx all by itself. Dx is dw divided by sec x tan x. And remember, w is secant of x, so we have dw over w tan x. So dw over w tan of x. And we get some stuff canceling. We get 1 power of w on top, canceling the w on the bottom. We get 1 power of tan of x on top, canceling the tan of x on the bottom. And we have an expression, tan of x times w dw, and we're stuck. It's a mixed expression. Mixed in terms of x and w. This is always bad. So I'm going to lightly cross it out. I want you to still be able to see it. Try again. So this time I'm going to let w equal tan of x. So dw by dx is secant squared. And then rearrange. So dx is dw divided by secant squared. So we have integral of, I'll write down the question again, integral of tan of x all squared times secant of x all squared with respect to x becomes, so I've replaced the tan of x with a w, so tan squared becomes w squared. Secant squared of x stays where it is, and then the dx gets replaced by dw over secant squared. And look what happens. This time we have a complete cancellation happening. The x variable is gone, it has completely disappeared. So now we have antiderivative of w squared. We can use the anti-power rule. We get 1/3 w to the 3 plus c, and we have one more step, just undo the substitution. W is tan, so tan cubed of x. I'll write a little bit neater than that. Tan power 3 of x plus c. So that one worked. W equals tan of x was the correct substitution to use here. W is equal to secant of x was wrong. It was wrong because it led us to a dead end, an expression that mixed the old variable and new variable together, and you never want that. Okay, here's a more interesting one. Cos of ln of x over x. We have two things we could try. We could let w equal 1 over x, or we could let w equal ln of x. I'm going to let w equal ln of x because ln of x is being plugged in somewhere. I know ahead of time that we're going to need dx, so I'm going to take the derivative. Derivative of ln of x is 1 over x, and then rearrange. So dx is equal to x times dw. And we'll plug that in. So when we do our transformation, we have cos of ln of x becomes cos of w. The x in the denominator, nothing happens to it for now. The dx becomes x dw, and the x's cancel. I'll make a quick comment about something. Sometimes we also need to isolate for x here. So w equals ln of x means exponentiate both sides. E to the w is equal to e to ln of x. Cancellation law. So that means x is equal to e to the w. And we may need to use that. We may need to substitute that into the expression somewhere to get it in terms of w. We didn't have to do that here. The x part canceled, and that's nice, but it isn't always so nice. And we can't necessarily just quit. We can't do the thing we did here, just give up and say, oh, okay, bad substitution, go back. We may have to charge forward. Even though we don't get a perfect, beautiful cancellation happening, we can still do some other manipulations and recover a better expression than what we started with. Okay, so this one's nice. Antiderivative of cos of w with respect to w. It's all one variable. The old variable is completely gone. The antiderivative of cos of w is sine of w plus c. And then we can undo the substitution. We get sine of ln of x plus c. Now this would be like a normal question that you'd see in a textbook or in a homework. It's just it's a classic problem. Here's another classic problem. Cos of the sine of x. And outside of that is a cosine of x. it's a bit messy. You have to look at it carefully. You have to read it carefully. You do have two functions that multiply together here. The cosine of x is one of the functions. The other function it's multiplied by is the cos of the sine of x. So you're looking at the part that's plugged in as a potential for the substitution. W is equal to sine of x. So dw by dx is cosine of x, and then rearrange. Dx is equal to dw over cosine of x. When you get the hang of these, when you do enough practice, you can start looking ahead. You can start looking at, well, what's going to happen in the next move? When I put that dx in there, look, I got a cosine of x in the bottom. It's going to cancel the cosine of x on top. I know already at this step that the substitution is going to work out well. Even ahead of that, this is f prime of x multiplied by the cosine of f of x. So if we recognize that at the beginning, we might be able to just write down the answer. But the method of substitution allows us to not see that right away. It allows us to kind of find it naturally, to find it without knowing it's there. So cosine of x times the cos of w, and I'll replace the dx by dw over cosine of x. The cosines cancel top and bottom. And that happens because we have the f prime of x times the cos of f of x structure. We have that chain rule derivative built into the expression. This is just like the last one. Antiderivative of cos of w is sine of w plus c. And then we undo the substitution. W is sine of x. We have the sine of the sine of x plus c, which looks weird, but nothing wrong with that. You can have a sine of x plugged into a sine. It's allowed. We already did this one. Did that one earlier. Saw that there was a trick for it. One of the warnings about antiderivatives is connected to wishing every expression that looks like these turns into a log when you take the antiderivative. So I'll show you that in the first case it's correct. You do get a log. In the second case, you do not get a log. You get the inverse power. So just be careful. Like, yes, there's places for shortcuts, but this isn't one of them. If you're thinking about skipping a substitution and just doing it mentally, be careful. Okay, so we don't have a function that anything's being plugged into. So I'm going to let w equal everything that's in the bottom. That's like all I can do. So let w, I got to write it somewhere else. W is equal to 5x plus 7. Then dw by dx is equal to 5. And then that means dx is equal to dw over 5. And we'll plug that into our antiderivative, 35 over w. And then the dx is replaced by dw over 5. We get a partial cancellation. 35 over 5 is 7. I'll put that out front. 7 times the antiderivative of 1 over w dw. And we do get a log function. 7 times ln absolute value of w plus c. And then we replace the w with 5x plus 7. So ln absolute value of 5x plus 7 plus c. Okay, so that is hopefully the expected behavior. When you saw the 1 over 5x plus 7 type of a function, you looked at that and you hopefully said that looks like the derivative of a log of something. And hope a log will come out, and a log does come out. The second one, this is not 7 times ln absolute value of 5x plus 7 squared. And it's not 14 either. And it's not 7 over 2 either. And it's not any combination of those things. It's not related to log functions at all. Let's do the substitution carefully. It's the same substitution as the last example. w is equal to 5x plus 7. And we know dx is going to be dw over 5. We'll plug that in. Look what happens. We have our 35 over w, but it's w squared. And we have our dx, which is dw over 5. That part's exactly the same. So 5 cancels. We got a 7 out front. 7 times antiderivative of 1 over w squared. But that's not law and absolute value of w squared when you take the antiderivative. That's a special case, right? We go back to the normal case. Any power except power negative 1. This is power negative 2. This is just the anti-power rule. So 7 times 1 over negative 1, w to the power of negative 1 plus c. So negative 7 over w plus c, which is negative 7 over 5x plus 7 plus c. And a very different type of expression. So don't take shortcuts. Well, there's shortcuts you can take, but this is not one of them. Don't guess what the antiderivative is. Just because it has a 1 over something feature does not mean you're getting a log function out of it. All right, you want to see something magical? Here's a testable, magical type of example, antiderivative of 3 over 2 plus e to the negative 7x. I'll show you why it's magical. What we did in the last example was we had an expression, something, constant over something, and I let w equal that. I'm going to do the same thing here and show you it doesn't work. Let w equal 2 plus e to the negative 7x. So dw by dx is going to be 0 plus e to the negative 7x times negative 7, e to the w times w prime. Then rearrange, or I guess e to the u times u prime, we already have a w involved. So we rearrange and we get dx is equal to dw, the negative there, 7 e to the negative 7x. And I got a slight problem. Integral of 3 over w. And we get negative dw over 7e to the negative 7x. And I mean, we could proceed, we can keep going, but we don't really want to. E to the negative 7x is equal to w minus 2. Go back to the original substitution, subtract 2 from both sides, and you have an expression for e to the negative 7x. So now we have this mess. We have negative 3 antiderivative, or negative 3 over 7 antiderivative dw over w times w minus 2. And we're kind of stuck. I mean, there is a way to proceed. It's a method called partial fractions. We'll talk about it later. But we don't need to. We don't need to have more advanced strategies thrown at us. All I'm going to show you is magic. It's a magic trick. So I need partial fractions to proceed. Instead of doing that, or a magic trick, we'll use a magic trick. We're going to use the most powerful, or second most powerful, strategy in mathematics for solving problems. We're going to multiply our problem by 1. So the antiderivative of 3 over 2 plus e to the negative 7x dx is equal to antiderivative of 3 over 2 plus e to the negative 7x times 1 dx. I'm just going to put a multiplication by 1 there, because we know that multiplying by 1 doesn't change anything. This looks dumb. Really dumb. Like, how on earth does this help us? What is 1? One is something that we could represent, let's say, as 5 divided by 5, or 2 divided by 2, or x divided by x. We can replace that 1 with an expression that is equivalent to 1. And that choice of what to use, a good choice, will lead to an answer that will kind of fall into our lap. A bad choice won't give us anything that's beneficial at all. The choice that I'm going to use here is I'm going to multiply by e to the positive 7x divided by e to the positive 7x. And as we go through the calculation, you'll see why that choice works. Use 1 is equal to same over same, as long as it's the same thing top and bottom. So I'm going to use e to the positive 7x over e to the positive 7x for reasons. Because mom said so, or because dad said so, or because uncle said so. And then after you see why, oh, okay, that's why mom said to do that. That's why. Okay, so we have 3 e to the 7x over 2 plus e to the negative 7x times e to the 7x dx. So that's going to be integral 3 e to the 7x over 2 e to the 7x plus e to the negative 7x times e to the positive 7x, just multiplying or expanding those bottom two terms together, dx. And then we can use exponent laws. We have 3 e to the 7x over 2 e to the 7x plus 1. Since e to the negative 7x times e to the positive 7x, the exponents add, we get e to the 0, which is 1. Well, I'll be a little bit more explicit here. E to the negative m times e to the positive m is e to the negative m plus m, which is e to the 0, which is 1. And now I'm going to do a substitution. I'm going to let w equal 2 e to the 7x plus 1. So dw by dx is 14 times e to the 7x, and then rearrange, so dx is equal to dw over 14 times e to the 7x. And look what happens. We get the integral 3 e to the 7x over w times dw over 14 e to the 7x. E to the 7x top and bottom cancels. I can take the 3 over 14 out front. 3 over 14 antiderivative of 1 over w, which is ln absolute value of w plus c. Which we can finally write, we can replace w by our substitution, 2e to the 7x plus 1, 3 over 14 times the ln of 2e to the 7x plus 1 plus c. It's nasty, but we didn't need any advanced strategies to do it. What we needed to do was we needed to do something simple. We needed to multiply by the correct form of 1. If the denominator term was, let's say, 3 plus e to the positive 7x, well, I would multiply top and bottom by e to the negative 7x. Try it out. So replace this question with that question, and it'll work out just the same. So you take the exponential term that's there, change the sign and the power, ignore any constant, and have 1 is equal to that thing divided by that thing. Simplify, and then do a substitution. It's a neat trick. And we'll stop here.